And Jim, I'll take notes and keep an eye on the chat.
Very good, thanks. All right, so 11:35. Why don't we go ahead and say that we've got folks here? Looks like the number of participants is kind of settling down. So we're in a session today where we're going to be talking about the solar Oberth maneuver case. And again, just so everybody realizes what's happening with this, this is what we're looking at in phase 3 of our study. So that's coming up in this probably early spring, late winter kind of time frame to start, and then we'll run that for several months until we see whether we have a valid concept or not. And I think, as everybody's aware, there are a number of issues associated with that. I did present some slides on Monday, and I don't know that everybody's seen them, so I want to just go back over those couple of slides real quick, just so everybody understands what the solar Oberth maneuver is and some of our concerns about it. And then I'm going to hand it over to Doug, who's going to be talking about the materials work and other work that he's been doing to help us define what a shield would look like if we were to do this case. So again, this is slides I presented on Monday, and you may have seen them already, but I just wanted to refresh everybody. So the question is, what is the solar Oberth maneuver that we're talking about? Essentially what it is gravity assist at the sun that would then accelerate us out of the solar system. The way you do that looks like something like this. We would launch on a 3-stage vehicle, probably an SLS, first 2 stages, and then the 3rd stage would be some kind of Centaur or something like that. We would have a spacecraft that we would carry with us, a solid rocket motor that we would then be able to fire at our perihelion. And we're estimating, I think that perihelion is going to be somewhere around 3 solar radii. So I show you on the right-hand side here, not a picture of the concept, but just a very early drawing that used a New Horizons type spacecraft, just as a concept and study and the ability to kind of give us an idea of what's going on with this. And you can see sort of one of the challenges associated with this mission. If you think of the sun being up in this picture, you can see there's a very large heat shield. I'm sorry, was there somebody had a question? No, okay. So you can see there's a very large heat shield that would be required to protect the spacecraft, the rocket motor, anything associated with the flight system from the solar environment. We know how to do this at about 10 solar radii because we're now flying this thing called Parker Solar Probe, which has a heat shield that performs this same function. But there are significant challenges whenever you go down to 3 RS, that I think Doug will be talking about here in a little bit. This heat shield can be made a couple of ways. One is to use just a high temperature material like metal, refractory metal or something like that, that would be able to withstand the temperature. And then there are other concepts Doug has been pursuing that would give us significantly lower mass that might bring this into the realm of possibility, and that remains to be seen. Some issues of concern for a system like this, as you can imagine, there's intense solar pressure there. That's one of the things we're fighting on Parker Solar Probe. And so any asymmetry in this heat shield is going to produce some pretty large torques from solar pressure. And so whenever you start thinking about that, you start having to think about how you're going to control a system like this. And frankly, with the masses that we're talking about and the size that we're talking about, we're probably also going to have, and what's not shown on this picture, is some sort of very large propulsion system that would allow us to provide the control authority we need to keep this thing pointed towards the sun, and also to do things like trajectory correction maneuvers for a very massive object, to be able to point to the location, to get to the location that we want to get to around the sun. Some other issues that we're worried about are things like center of mass shifts during the solid rocket motor burn. Gabe has looked at this in considerable detail, and there are some very significant torques on the system unless you do something like add a ballast mass. And even then there are issues. So one of the things that we get to whenever we look at a system like this is also is not shown here, is how do you balance the mass of that big heat shield that's out, sticking out from the center line of the vehicle, or the center of gravity of the vehicle, which again is going to add mass to the system. I've already talked a little bit about the heat shield having to survive higher temperatures. I'll let Doug talk about that. Let's see, I've also talked to the balance mass. And also the other thing that we have to deal with here is that as you're adding things like heat shields to the system, we're really seriously constraining things like where we put our star cameras, where we put our thrusters, even to the point of, if you look at the nozzle of the solid rocket motor, you can see that the heat shield extends beyond that. It has to. And so are there issues with the plume from the solid rocket motor and effects from the heat shield that we don't understand yet? So there are some very significant problems that we gotta solve if we want to use a maneuver like this. As I say here, the concept sounds simple. I mean, it sounds like a great idea. We use gravity assists at Jupiter, and that's our primary trajectory. So why couldn't we do it at the sun? It's just really all these other things that are going on that make this such a much harder concept. And so I'm not going to talk to the temperatures here on the right-hand side. I did that on Monday, but I think Doug will be covering sort of what is the environment that we got to plan for, what are the materials that he needs to make this heat shield. And really this information that Doug is providing is key to us being able to look at this concept and develop something that might be a realistic heat shield. But ultimately, this is something that would have to be developed, much like we did for Parker Solar Probe. And so there would be a development effort associated with a project if we were to take this option. And I think it's a high-risk effort at this point. I think that's pretty clear. It is something that, with enough money and enough time, probably could be done. The question is whether it could be done in the time frame that NASA is asking for this mission. So with that, I'm going to stop sharing now that I've been enough of a downer, and see if we can have Doug show us what they've been doing. I do know that they have. I do know that they have had some significant progress, and so that's very encouraging. And so, Doug, I want to make sure you have plenty of time to talk about that.
Okay, my name is Doug Mehoke. I am watching thermal as far as Interstellar Probe goes, and I'm actually also leading the development of the solar shield effort. And so again, a key point that I will make early and often during this discussion is, as Jim noted, this is part of a larger effort to actually do planning on a interstellar probe type of program. So this is less what is maybe theoretically possible in terms of what are the directions that we could actually go and what do we actually have to do to move in those directions. So we are not building anything right now, but we are seriously thinking about what are the options and what are the challenges for that kind of thing. So let me get into that. Okay, this is the same chart that Jim had up. I have a big red note down here saying that this is New Horizons spacecraft. So it is not the Interstellar Probe spacecraft or a study associated with that. It's just something so that we have something to talk about. But it does have some key features. You got a kick motor, you got an RTG, you got a big antenna, and a spacecraft. So you're trying to package all this stuff into the umbra cone that the heat shield is producing. As we get closer and closer to the sun, that cone gets bigger and bigger. And so, at solar probe distances, we have a 6-degree cone. As we get into 3 RS, that's getting up into the 30 degrees cone. So, how big that shield gets, is a function of what it's protecting. And as the spacecraft gets bigger, the shield gets even bigger. So mass is an issue. Jim talked about attitude control authority. The whole point of going to the sun is having a big kick when you get there. And so you have to have, something that's, giving you that big kick. And again, that something would like to act along the CG of the system. And if you've got, thousands of kilograms holding off to the side, it's going to be hard to do that. And so as the shield gets bigger, the system becomes untenable that way. You also have, related issues, plume impingements. You have thrusters, big thrusters, little thrusters. Those thrusts are going somewhere. How do those thrusters act when you have a system where they're being blocked at one level and not being blocked on the other side? And then there's the big question about test as you fly. So, you know, you can see something like this. You are not going to be testing this as you fly it. And so how do you approach that whole problem? There are things you can do, things that become more questionable, and then things that you can't do. And the question is, as you move towards a real design effort, is how do you separate all those different options that you have to look at into the ones that you do have the time and the money to look at. So one of the things we did, and this was during the 18 studies, we did look at available materials, and we'll talk about that in a second, but you know, the only materials that really exist at these kind of temperatures are, you know, the heavy refractory metals. And if you start making a shield up here out of tungsten, it gets so heavy that, you know, it is not even worth talking about moving forward along that path. So we're really talking about specially tailored materials and design options for a shield to enable this approach. And we're going to talk mostly about two things: materials and optical properties. So again, talking to interstellar probe is, again, from a thermal point of view, from a solar shield point of view, is extremely exciting, because the question is not, you know, building a shield to get you to this sun distance. That was the solar probe. The messenger questions, there was a trajectory. You got so close, you needed a shield to protect the spacecraft at that distance. The real question is here, how close to the sun can you get? You can see on the chart, here's the solar probe line, and here's the options that you have going for interstellar probe to see how close you can get, and what are the design drivers that are keeping you from moving closer, and what are the options for beating down some of those design drivers. This is all complicated by the fact that we're moving into a design environment where there is no, you know, materials do not exist, analytical methods don't exist, testing efforts, testing facilities do not exist, you know, that you can just put your materials on and have them. So the key point here is very expensive to move from theoretical ideas into a practical design. And so we're not moving into the practical design, you know, at this point, but we are thinking about that. And the question is, how do we think about that in a way that allows people to make decisions about, you know, whether things can actually be done or is not worth going off in that direction. So we want to be able to have down select ideas in some sort of rational manner. And the question is, how do we do this in an area where we don't really have any experience? And so again, emphasis of what we're going to go through is, during this discussion, is talking about some of the practical issues. Again, we have done this, we did go through this effort on solar probe way back in the early days before solar probe started. It was a similar type of situation where solar shields had been looked at and discussed for a solar probe kind of mission for decades, and you know, they had not really gelled. And then the question is, what happens, you know, to make them gel? And there's a bunch of things, but the you know, there is a process that you have to go through to go from nothing to something that has some realistic chance of moving forward. I have a chart here that just to give you an idea on two different things we talked about with solar shields. I do not have a reference on this chart. I was looking for that this morning. I will find that and add that on to it. But this is a paper that was written basically comparing reentry shields. And there's two parts that you're talking about in a reentry shield. You're talking about the peak temperature that the surfaces get to, right? So that is defined by the peak heat flux. And you can see where we are on an interstellar probe at 3 or 4 solar days. We're in the mid-range, and we're not close to what, you know, people have seen, and we're more than other people. So I mean, you would say this is in the doable kind of range. But the other part is the total heat load, how much heat has come into the system and has to be dealt with by the system. And you maybe not be able to see the exponents down here, but this is 10 to the minus 5, 10 to the minus 6. And we're up into the 10 to the 11th on solar probe. So this is a new kind of heat shield. It has to protect for the high temperatures, and it has to do this for a long period of time. So we're past the point where ablative systems can handle that. They can handle the temperatures, they don't handle the pulse. And there's a lot of other issues that we deal with, you know, that are different from reentry in terms of Oxidation is important in the reentry system. Earth entry, anyway, is less important here. Radiation is probably more important here. And the mass that we just talked about, where the shield, by definition, is not symmetric around the spacecraft, and so that shield mass and where it's located is extremely important in this kind of situation. So let's start off. Again, for the interstellar probe, we're talking about our area of interest is kind of between that 2 and the 4 solar radii. At 4 and up, I will call it the bang for the buck is probably not worth the effort for doing all this. And at 2 is somewhere in there, there's a realistic limitation. You're just not going to do any better than that. So kind of as a graph here is showing kind of what the temperatures are as a function of optical properties. So again, as we move close to the sun, the temperature of the surface that's looking at the sun is determined by its optical properties. That is the solar absorptivity and the IR emissivity, how heat's coming into the shield, how heat's leaving the shield. Most of that heat is coming in the front and going out the front. There is some energy that's going down into the system. And again, the larger that is, the less the shield is working. And so what we're aiming for is a shield that is basically adiabatic on the front surface. And so one of the questions that we get into is that, do we have values for these optical properties so we can determine what temperatures we are? Once we have the temperatures, we have properties for the materials that are going to be used to build the shield so we can see how there's effect, how the design is affected by those. Optical properties, we'll talk about them some more, but they are determined by a variety of details having to do with the surface itself, but then how that surface degrades over time. We are going into a space environment, there's radiation, there's temperature, there's other things that are going that will cause the surface to change. By definition, optical alpha, the solar absorptivity, which is the one in question here, tend to get worse as they degrade. And so you see this in regular spacecraft where there's a beginning of life and an end of life property. And again, the end of life property is getting worse. Temperatures are going up. We have a limited amount of ability to deal with this. We also have the limited capability of measuring these things at very high temperatures. And so again, the more uncertainty you have in your ability to measure, your ability to design, the more margin. As you put more margin on it, temperatures go up, and you have, so it becomes an extending problem that has no solution to it. So basically, if you look at the boxes here, there's kind of 2 boxes that we would like to be in. From the materials property side, we would like to have a low optical property, so we were keeping our temperatures low, and we had materials that we could kind of work with. Materials that we can kind of work with are, carbon up to the mid 2000s-ish. Again, I'm using C. We're supposed to be using K in all these, but didn't do that. And then, there is a material that's taking you down to what I will call a known material, which is titanium. Titanium has a functional upper limit for a structural system that's somewhere around 600 or 700 C, and that's the point where the strength is dropping off so fast that it's no longer useless. It's no longer useful. And so again, from a materials point of view, we are interested in having good optical properties that would keep us down. This is a 0.1, 0.2 kind of range. On the thermal side, on the optical property side, understanding that it's difficult for us to understand what these are, for these to analyze them, measure them, and understand how they degrade, we would like to have a big range. And so again, this is the work that was, temperatures are the temperatures, but one of the big things that was done in the early days of the solar probe shields was to try to figure out what an optical property range would actually be, going close to the sun. And you see numbers again, somewhere in the 0.8 to 1.1 kind of range. Again, bigger numbers are getting hotter. It's important to note in here is that, in a traditional sense, and I think we'll talk about this, we have different parts of our system. We have the front surface. Again, this is on the thermal side. We have a front surface, we have an insulating layer, we have MLI, and we have a spacecraft. So the spacecraft and the MLI are normal. Those are used all the time. They have temperature ranges that are kind of listed where they can be. The based on solar probe, we have an insulating layer, that on solar probe is getting us up into the 1400 C range. That system, those materials have the capability of likely going up into the, around 2000, and we're still way away from that. So we need this other front surface that's taking us up not only to the 3000 degrees, but knocking down the temperature. So something has to happen to get this 3000 degrees temperature down to this 2000 temperature below that. And again, as we move from the bottom up, we're moving from situations that we know to situations that we don't know. And so again, the design intensity, the time, the effort needed to work that kind of goes up. On the mechanical side, they have a different problem. So the mechanical effort is, there is a front surface that has to be supported off of something, which has to be supported off something, which is supported off the spacecraft. As that front surface gets really hot, those supports that are holding that front surface to the insulating layer are basically at the same temperature. And so they need to be strong enough to hold that front surface up, as that, if that's a tungsten surface that's raised, it's weighing thousands of kilograms, you can see how that would be a problem. These front surfaces would become so involved in so many that they would be basically become a solid surface themselves. And so then all you do is take this front surface temperature and you move it down to the next surface. And again, the insulating layer can't survive that surface, and so again, that's where it ends. But if you can have a front surface that is of a low mass material, right optical properties, right thickness and stuff, so that it can survive and drop the temperature to the point where you get a top layer, then you can have lower types of masses. This is kind of the situation that we saw on SBC, that little cup, that's Faraday cup that's sticking out next to the solar shield on solar probe, where we had a niobium front shield, and there was a considerable effort went into how few and how small number and how lowly thermally conductive these front supports can be. You get back to the insulating layer. The insulating layer, again, has to support everything above it. So it's supporting the front surface and all those supports as a structural element. Again, one of the big issues on solar probe was, if you're using a carbon-carbon foam, a sandwich kind of material as a structural element, that does really well from an insulation point of view, but it doesn't have a whole lot of strength to carry large loads into it. So again, you need to have low mass on the front surface, and you'll be able to spread that mass into the insulating layer that's necessary at the carbon-carbon front surface that's helping, moving that loads into the sandwich structure. Far down, you have what I will call a regular structure. So this is a titanium truss or something like that that's holding the weight of the whole system off the spacecraft. It's supporting the launch loads. It's supporting the thermal loads that are happening during orbit. And so it has to be, it is carrying a large amount of mass, no matter how you minimize this kind of thing. And that has to hold these things in this cantilevered design that you're seeing, because the shield will not be on top of the spacecraft, it'll be off to the side somewhere. So you have a large structural load that you're carrying at launch, and you're also having a large thermal load that you're carrying during the mission. So all these materials have CTEs, they're expanding, they're retracting at different rates. And so you can see how these front surfaces are expanding dramatically. And again, on solar probe at those temperatures, we were seeing a expansion of the shield that's on the order of 1/4 of an inch, and the front surface would be even there. So you need to have flexibility in these materials and also strength. And again, you have to be able to bound these in the ways that you have some understanding for what their limitations are, and then you need to be able to do the analysis that shows that the system will not only behave, but that there's positive margin for all cases. So you have to have material properties. You have to go through the regular analysis case, which can be seriously involved. So we'll talk about material survivability. The primary driver for the shield is mass loss. At these temperatures, the vaporization of the material is going on and is causing them to lose thickness and lose mass. There's a bunch of curves up there for these materials. There's legend. I'm not sure why it got dropped off, but the legend has one more. There's 6 lines here. There's only 5 lines here. The bottom legend is tungsten. So tungsten is, if you're just looking at materials that work, tungsten is your material of choice in the sense that it has a very low vapor pressure and it has, I guess that's its main claim to fame. It is also extremely heavy and it's not a design material. It's brittle material, it's a refractory metal. As we get up around the 3000 degrees, if you say I have a certain temperature profile that I'm going through for a certain time, and you kind of back calculate that out to figure what allowable mass loss rate you can have in the centimeters per second range, it's kind of in this 10 to the minus 7, 10 to the minus 6 range. And so this is, again, it's a complicated question because, these are all things that you don't know all that well, so you want to have margin on them. How much margin you need is kind of a function of how well you know the answers. And so you have curves up here, how well do you know those curves? And then as you build the front surface up and it becomes heavier and heavier and heavier, it becomes harder and harder to support it, which allows, more structure in there, which causes the temperature to go up. And again, it spirals out of control. So again, bunches of questions in here, but one of the questions is, what information do you have and what do you need? How well can you get that information and what kind of margin do you have to hold when you're thinking about design issues? So generally speaking, when we're talking about mass loss rate on the shield, we'd be talking about something that is like an order of magnitude. So this is not a factor of 2, this is a factor of 10. It might be a factor of 100. It just kind of depends on how well you know the numbers, but the margin is the key issue here. So just some curves. So this is on carbon-carbon. This is all data that you can find in the literature. And you can see this is the blue line is the line from the previous page. Went through and tried to pick out, carbon-carbon vapor pressures, and you can see there's other points that are on the line. Some of them line up pretty well. Some of them don't line up pretty well. Some of them are a little bit off. The ones that are seriously low are people were looking at carbon is coming off as carbon. It's also coming off as C2, and so these are lines down here are for C2, and those are coming off at a much lower rate than carbon is, and so again they're just up there in the plot. But you're seeing, so you have some flexibility in here or variation in here that is at least in the order of magnitude range, and it may be higher, and again it's getting worse as you get higher. A lot of this testing was done in the early 50s and 60s, and again there is not a lot of testing facilities out there, right? So if you wanted to have, if you say I have this piece of material and I want to do the measure its vaporization, up into the 4000 C, 4000 K range. That's not a trivial test to do, and there's not a facility set up so that you just go give them the material and they give you results. So there's time and energy put into just figuring out how to do the testing, what testing you have to do, and how you verify those testing. Again, one of the big issues is how you measure temperatures at these temperatures. At these levels, one of the big things that you're doing when you're measuring temperature is you're saying, I know what the vaporization rate is, so if I can measure the vaporization rate, I know what the temperature is, but that implies you know what the temperature is too. So again, we don't have a good way to put error bars on these numbers. There's not a lot of data out there, and again, uncertainty drives the margin, and so as you put margin here, the whole design gets bigger and heavier. Optical properties. And so again, temperatures on the front surface are driven by optical properties. Again, this is how the energy leaving the sun is absorbed, reflected by the surface. You can see there's just some curves here. We're talking about range of wavelengths. The visible is happening on the short range. We have IR that's happening in the kind of the longer range. These are all curves that we took during the solar probe days for a variety of different things. We were looking at different kind of pillars and stuff like that, but they, the point is that for a given kind of material, you can get a given reflectances. You get reflectances that are going on in the short wavelengths that are due to the pore size, the porosity, the things that are, how you use your plasma sprayed kind of coatings, and so how you sprayed them, and the particles that you use, how those turn into splats on the scene. So this pore size is important. One of the big things that you do in ceramics is you try to get rid of pores. In a reflective system, you were trying to encourage pores in these short wavelengths because that's where the reflection is happening. But then you have to worry about how these things change, right? Because again, it's not the idea that I can, if I have this coating and I put this coating into an oven and I heat this coating up to whatever temperature I'm going to, it will have a new reflectance profile when it comes down. And what will be happening, one of the things is that what's happening in the pores, the porosity at the small end change, the material relaxes. I have my pores expand out, my grains grow and things like that. So I have a different reflective structure. So my absorbance goes down in the low wavelength, and again, when my absorbance goes down, my temperature goes up. Usually, again, we have, when we're talking about solar absorptivity and IR emissivity, we're talking about things that are happening at hot temperatures on the absorption side and things that are happening at relatively regular temperatures on the emission side. We don't have that case as we get hot. As we move into the 2000s and 3000s of degrees.
All right, so let me go ahead and share my screen. All right, so you should be able to see my screen now.
I cannot.
Hear me?
Is someone presenting?
I think we lost him.
Okay, we'll continue on. Anyway, so the question is what kind of range you can go to as the temperatures of the surface move towards, 3000 C. There's a significant overlap between the solar energies and the emissions energies, and so those two systems go. As these temperatures get hotter and hotter again, the alpha ray is moving towards 1, and so how fast it moves towards 1 is a function of the material and how hot it gets. Okay, so one of the things that you do is you figure out what you think your material properties are and how they're going to change. So again, there is a beginning of life optical property that you calculate by doing analysis of the material, doing tests of the materials and things like that. And then so there's analysis that can go on here. There's testing that can go on here where I measure material. If I have a given material and I make 15 of those samples, what is their variation? I'm covering something that's covering multiple square meters. And so I'm using material, how often does that material change from location to location? As I produce this thing in large surfaces, what are my variations just due to defects, due to processing problems that are going on in the material? So there's a whole range of process that you go to figure out what your beginning of life temperature is. And then you say I'm going into space, and so I'm hit with a temperature environment and I'm hit with a radiation environment. What happens to these materials as they get hot and as they're radiated is that you get color centers in them. Color centers, there's a lattice structure here. You're displacing ions from where they normally sit in their lattice, and those leave behind localized electrons, and you get a little darkening of area there. Again, the darkening area, makes the alpha go down, makes the temperatures go up, and so it is very important. When you do these type of tests on the ground, you see what's known as oxygen healing, where you would put your coupon in, you would irradiate it, you would see a darkening of that coupon. When that darkening of that coupon, came into contact with oxygen, with the atmosphere, it heals and it goes back to being a white coupon again. Because again, you're replacing those ions that were left with ions that are being put in from the air. That can happen slowly. It can also happen very quickly. And so again, you're getting this question about how, if you're doing this test and then you're measuring your optical properties post-test, is that correct, or is that just effect of the healing that's gone on? We will not see this type of healing generally in space. There is some sort of atmosphere around the thing, but generally speaking, we're not seeing the kind of surfaces. We don't have the kind of materials or quantities of them to actually heal these surfaces, and so you may not see the degradation in ground testing that you're going to expect in orbit. So sometimes you have to do this stuff in vacuum. That makes it even harder. But again, if we had a, so we're trading off materials. We're trading off, if the more uncertainty I have in my optical properties, the more I would like to rely on my mechanical properties and go through a wider temperature range. The more uncertainty I have in my mechanical properties, the more I would like to rely on my optical properties to keep it down into a more realistic temperature range. So part of that is the material discussion. Part of that is the testing discussion that talks about how accurately you can simulate these and test, and how much margin you have to put on this. And so again, in the solar probe case, we wound up with numbers that were kind of in the 0.2 range. We had numbers that were in the kind of 0.1 range that were from all this darkening. We had a 0.1 margin on here. So we wound up with what we thought was our launch condition case of a requirement that was a kind of about 0.4. And we were using a design alpha over E of 0.6. And so that gave us what I will call a healthy amount of margin. Whether it was enough, we'll see, but we were not trying to push it right to the edge. And so having enough margin in the design to account for those things that you don't know or you're going to get hit with is important. On the mechanical side, it's the similar kind of situation where mechanical, you have material properties. In the system, you have a variety of materials. You have some materials that are testable, some aren't so testable. You can see, again, this is just something I pulled out from the foam test. So this is foam tension. These are in PSIs. And so again, the foam can't deal with a whole lot of stress. This has to do with that insulating layer, the thing that's dropping the big temperature between the front shield and the whatever surface is pointing at the spacecraft. Again, when you're doing this analysis, analytically, you're saying I need to have some understood heritage, and the standard thing you use is B-basis allowables, and that says I have a 10% chance, or a 90% chance of having being above the 10% bottom limit of the material. So I can use this in an analysis and predict margins and have those be meaningful compared to our mechanical expertise that we are traditionally used to. As you try to do these tests, there's a process you go to take that statistics and turn them into B-basis, and that has to do with the variation in your properties. The variation in your properties is driven both by the variation in the materials themselves and by the variation in your test conditions. So as your test conditions become more and more difficult, you see variation that's just due to the fact that it's a very hard test to do, and so those drive your cases. And these were the foam, what was a material that was done when we were doing this with the bond line between the carbon-carbon and the foam. We're actually winding up with negative allowables on this because the uncertainties in the test were so large that they did not turn into statistics too well. So then you get into a different question. Can I approach this in a different way? I am not going to, this would be true on solar probe, this would be true on interstellar probe. You are not going to be able to do a full up test of the shield in flight-like conditions. And so how do you come up with something that gives you enough confidence in the design that you can move forward in? And again, this was one of the options that was done, is that you look in this top picture, here's a 22 by 22 analog coupon solar shield made, and here's the flight article. Again, this is 9 feet across. But if you look at, in terms of, this is due to the hot case, I'm getting a hot front surface and the shield is puffing up. They do this upside down, so this is backwards, I think, from the actual height. But and so the the top phase sheet is expanding, the bottom phase sheet is in compression, and you're seeing loads in here. But the loads that you're looking at in the full size shield are on the same size range as the loads you're seeing in the smaller article. So the argument then is made, if I did this testing with a smaller article, I can test that in a flight condition, since I can put a huge temperature and a huge temperature gradient across it, and I can see how it survives. I can do this for multiple cases to make sure that it can do this multiple times, and I can verify that the test that way. So the use of subscale analogs for flight testing is critically important when you start thinking about moving towards a design for an extremely complex system that will not be able to be tested in the flight condition. So again, we're talking about then solar shields. And so the concept here, which is similar to what was done on Solar Probe, is that you would have a spacecraft down here, you would have a supporting structure underneath that. Again, keeping in mind that there's lots of mass up here and there's lots of loads on launch and stuff. The big job of the supporting structure is to minimize the loads that are input into the foams and the carbons and the shields up at the top that have lesser ability to take loads. And so the shield is, I will call it, a relatively involved truss structure or something like that. And this is made out of something like titanium, which limits your upper temperature at that bond joint to something, again, that's in that 600 or 700 degrees. You're dropping another 1,000 degrees off the insulating layer. And so these top surfaces, are surface in this, in this concept here, this is similar to what used to be called a V-groove shield. It's kind of the thing they're doing on NGST, where you have layers of material, and there's heat coming in the front end, and basically some of that heat is drifting out through the sides, and that allows the temperature to be dropped. The more layers you have, the more heat you have, and so eventually you get to the point where you can drop the temperature down to what a 2,000-ish range, where you can start using a regular shield. Use that regular shield to drop the temperature down to a 600 degree, where you can use that titanium, where you drop that down to the spacecraft, which is again running kind of at room temperature. So again, you're limited to at the top side, again, material-wise, just to refractory metals or metal carbides, which are dense and brittle, so they're heavy. And so again, that was the part of the earlier study, is that as this top part of the shield design becomes thousands of kilograms, it loses its intention right where. So the bottom curve is showing that for different materials, if you're looking at this from a material survivability point of view, you're saying this material has to survive through this hot pulse. There are materials, niobium, tantalum, tungsten, that can survive the hot pulse. So their limitation there is basically how thin you can make them. There's a limit to that. And so they can get into some temperature, in which case they kind of just disappear. And so again, tungsten is the only material that's really taking you all the way down kind of in that 3 RS range. Carbon, a good material of choice, mechanical properties and temperature stability does have an upper limit where it's disappearing all by itself. And so again, if you're just making the shield thicker and thicker and thicker to allow for that vaporization, eventually it becomes so thick that the mass goes. So if you're looking at, these are kilograms per meter squared, and we're talking about tens to hundreds, and we're looking at a shield that's tens of meters in square, you're talking about huge masses here. And so again, something different needs to be done. A related comment to all that is, if, let's say, you could build something and you could test it, there's the implementation and verification. So how you go into this problem. We did a lot of work on Solar Probe, going to different places and trying to get things hot. And lots of people, upper end is around in that 2,000 range, because that's kind of where the interest has always been. So you have, Glenn, who are, these are using heating elements. We set up a lamp system down at Oak Ridge. You're trying to do, not only are you trying to do the test, graphite heaters, radiant lamp heaters. We want to do this whole test in vacuum. Again, the vacuums you get are kind of difficult, so we're not talking about high vacuum usually, we're talking about medium vacuums. And again, medium vacuums have, when we were testing at Johnson, we would see charring of the carbon that was in the system. That was probably in the couple of torr vacuum levels. We have a vacuum furnace at our place. They had a vacuum furnace up at Hopkins that had different vacuum systems on it. So we're talking about between a 10 to the minus 3, 10 to the minus 5 torr. We were getting different results just based on the vacuum pressure that we would see in the system. Again, there are materials in there. If there's some oxygen in there, the oxygen is doing things. And so you have to set up this system and you have to run with it so you know what it can do. We did a good amount of testing down at XCEL, which kind of broke away from Auburn. Here's their chamber down here where you're just putting basically a large flux into the system in vacuum and measuring both the temperature and again, optical properties. You cannot do this testing with ArcJet. You can get up to the right temperatures, but again, ArcJet is just getting up to the right temperature. It doesn't help you deal with any other parts of the design. And so one of the big things that you can do is laser testing. And again, there's some places where you can get good sized beams up into these ranges, but again, those testing places have limited availability and you're limited on coupon size. So there's a bunch of, you are not taking the full size system into a test fixture and running it. We're taking different samples in and you're starting from smaller samples and working your way up to larger samples. So here is kind of the process that we went through on Solar Probe to qualify the shield. Again, this, the Solar Probe as a program, functionally started kind of in the 2009 timeframe. There was a whole work that was done at APL before that. And there was a whole bunch of work that was done at JPL before that. And so each one of these steps, moves you forward in understanding part of the system, understanding the testing of the part of the system. But then you get to PVR and you say, I'm ready to go. I have a TRL6 unit that I have shown works, and now I have to qualify this testing. So you're doing a qualification and acceptance test, and you're not doing this as a system, you're doing this as pieces. And so you do this as material testing, you do this as analytical modeling, you do this as life cycle testing, subscale testing, and full scale testing. So you can test large shields cold. You can take them in the chamber and you can get them cold. Then you can tail subscale things hot, assuming you have a chamber that gets big enough. Our size scale that we were kind of limited to, there was kind of that 2 feet by 2 feet size. And so again, we built little coupons. We built a TRL6 unit. We built a qualification unit, and then we were ready to go for the flight sphere. But this whole process, was put together kind of in that PVR timeframe where you say, this is the. If we go through this process, we will have considered our system to be qualified for flight. And then you have to get your review board to buy into this because then you're going to follow this process. And it becomes difficult later on to say, well, we can't do this test, so we're going to do this test and start of it. And so, there's a thought and discussion between the team and the review boards about what a verification process is actually possible here. So again, the big topic here has been theoretical versus practical. So as opposed to papers and things like that that are discussing different things, and here's one of my, this has been a favorite discussion point, is that if you go into the literature, you can find a paper that says I have a material that has a it has a 0.1, it doesn't matter, but 0.001 absorptivity. So I'm basically absorbing no sun. All this energy that's coming in is being reflected. You can find papers, that go anywhere from that up into much higher values. And as you saw before, that somewhere in that 0.8 to 1.1, if you can get into that region, you have some options. If you need to be in that 0.1 to 0.2 range, then you have to go through all that effort to kind of show that the material will stay in that range. I can build a big enough size to work to operate in that mode. Again, the interstellar probe operating environment is well above the range that we have experience. We have test facilities in And so all those considerations become part of the discussion process of how you move forward. You're moving forward both on the thermal and the mechanical side, where they each have their own issues, and in some sense they're fighting each other. As the uncertainty in one area goes up, you cause problems that in the other area that feed back into the first area. So as things get hotter, the structure becomes more uncertain, so it needs to be more, and then it causes temperatures to go up. So there's the same questions that you run into. How hot will the material get? How does that change? How does that degrade in space? How does it mechanically stay in place? And how much mass do I need to do that? And what material do that? So the result of the 2018 study was that with existing materials, you were not going to get there. You either had to rely on materials that were so heavy that they were fundamentally not going to work, or you had to rely on optical properties that were would be so difficult to verify that you were not going to get there. So finish this off, we have been doing some work with a company, Advanced Ceramic Fibers, on developing new materials. And the idea here, and again, there's lots of proprietary things in here, and I'm intentionally not providing any real information, hopefully. But we're looking at the transition metals here and combining those with carbon in such a way that we provide a carbon-like material that's got low mass, it's got some flexibility, and it's got strength up into very high temperatures. Again, big part of that effort has been trying to get things to temperatures, and again, we have some idea that we're getting things up into the above 3,000 and surviving a metal carbide fiber. There's densities here where you have potentially operating in this lower density regime, which is good from the mass, which is good from a shield mass point of view. You're doing in such a way that you have keeping some of your mechanical strength of the carbon. How much you're keeping, again, is a big question. You're having a structure system where this material system that you're building up is still really acting as a composite. So there's a matrix, there's a fiber, and you can see in this case they're pulling these parts out, and you're seeing that there's still fibers in here, and there's still a matrix in here. So you're still seeing that composite structure that is giving you some flexibility, and you're doing all this in such a way that we are taking carbon as a material up much higher than it would otherwise able to go, and we're doing at a density range which is not really which is in the range of possibility. And so again, similar chart is that there are multiple materials. Again, this is, I think, tantalum carbide up here, the vapor curve, but you're seeing temperatures up in the 4,000, 3,000. So there are materials that get up this hot. Again, proprietary processes and materials, going through the process of using those materials to suppress the evaporation of the carbon, which extends its operating temperature to much higher levels. Much work needs to be done there, but there's potential there. And again, this is a metal carbide over a carbon kind of system, so you have potential for self-healing as carbon comes out from the system. It's reacting with the layer, and it's protecting barriers, so you become less sensitive to what's actually going on, defects in the material, because in some sense it's self-healing. So we have to have some data that appears that shows that this thing works into the 3,000 range, and may be extendable up even into the 4,000 range. You're again limited by the materials themselves. So again, early work is done, but the takeaway from all this is you could get a metal ceramic matrix system that's making a composite-like material that would allow you to go to these ultra-high temperatures, with some idea of them actually, being in solution. So we're kind of very excited about that. Conclusion. So again, the big takeaway is that again, in an interstellar probe context where we're actually thinking about doing things and making decisions about what things are worth doing, what things aren't worth doing, the idea between theoretically and practical is huge. You know, what is, do we have a chance of working, and what is an idea that, you know, if somebody does some work will turn out to be not worthwhile. There's many ideas out there, most of which are practical, some of which are practical. And so again, how do you differentiate those? Which one you want to put your time and money into? Just the testing of these things is extremely involved in terms of, you need to be able to get the very high temperatures, you need to have good vacuums, you need to have large areas, a bunch of things you need to do. And so the question is, you know, how do you do this? And again, this takes time. Again, if you look back at the Solar Pro program that was done in the early part of the Solar Pro program at APL, and, you know, a much longer time period that was done in the Solar Pro program at JPL, you know, time is necessary to understand the materials you're dealing with and what their limitations are. And then as you get these new material solutions, either on the material side or the optical property side, you know, they need to, you know, have some time to develop those in terms of testing those to see how they work and what they work. And then once you do all this, you know, then you still have all the problems that, you know, Jim talked about at the first part of this, you know, which is the practical implementation of this on a real solution. And you start talking about, you know, thrust control and packaging and all those kind of things, which, you know, this allows you to start that whole process. And anyway, that's the discussion I have. And so I will take any questions, or we can move into a general discussion about the whole idea of interstellar probe shields.
Great. Thanks, Doug. Yeah, we have had quite a bit of discussion going on in the chat, so I thought we'd just spend a few minutes kind of running through that, and then we'll open up the floor for additional comments or questions or discussion. The first of these, I think, came from Wayne, who is interested in the sublimation and whether the shield mass is decreasing, because obviously for folks like Gabe and Wayne, they'd have to account for that in any of the control systems that they got to deal with, trajectory management. So do you know what the sublimation is for the shield?
Well, yeah. That's a margin question. So what we would say, for instance, if let's say that you had a you know, shield that had a certain thickness, in order to be confident that we would not be losing that shield, we'd probably be an order of magnitude away on the sublimation rate. So I think it's probably likely to say that you know, we would have you know, the mass of the shield would not change should not be assumed to be changing dramatically over the time where we're doing the closest approach.
Mm-hmm. So I think we'd have to look at what that means in terms of small forces, for instance, that would have to be accounted for, especially if you're integrating that over a long time for a pass, right?
Agreed.
So that's something that would have to be analyzed, I think. All right.
But again,
yeah, go ahead.
Just to note that, you know, for these materials, for these sublimation rates, you know, we have a spreadsheet going that basically lists how much of the material they lost, and that was one of the curves kind of that I had up for, at least in the for that material that we're talking about. You know, we're talking about losing a fraction of a toe, you know, in a layup.
Right.
But yes, we can do that.
I'm curious about the small forces comment. Is that on par with the solar pressure, or is it a different order of magnitude?
Oh, it would be a different order of magnitude entirely. The solar pressure is going to dominate. All right, let's see what else. Ralph had a question about our experience on Parker. If one reduced the margin in that design is flown to zero, how close could you get to the sun with the current design as built? And obviously, he comments, we never go with zero margin. I think it's really just a question of feasibility more than anything else. So how close could we get if we just took the shield and went as far as we could?
Right. So the comment there is that, you know, we were saying that kind of in that me talking, but we believe that we could, good optical property and stuff, we could get a system that was capable of surviving down to 3 solar radii with a, oops, I lost it. 3 solar radii with enough margin and things to make the system survivable.
That's what the
Probably.
What about with the carbon-carbon? It looks like your plots there are considerably different, right?
Carbon-carbon, assuming you could get good optical properties. So, on a regular carbon-carbon system with a regular shield, so this is kind of solar probe, the original solar probe that had a cone on it was going down to 4 solar radii.
So just by context, the system we're looking at right now going to 9.8 solar radii is at about 1200, 1300 C, is that right?
Yeah, so that's basically, a curve that's right in here. And so, if we're going up here, it's probably in the 4 range.
Yeah, so you could get lower, but it's not going to be as low as we'd like to. That's the answer to that. All right.
Right, and again, just as a comment on that, one of the issues on the solar probe one is the limiting item there, vaporization, is not the carbon-carbon, it's the aluminum coating that's sitting on top of that.
Right.
That disappears somewhere in the 1700 range.
That's fair, yeah.
That could be changed to a zirconia coating, right, which would be higher temperature.
Okay, we spend a lot of time and energy doing it. So if you get you can change to a different coating, and then you come along, you have to talk about the optical properties of that coating, which causes the temperature to change. And it is likely that the zirconium coating would be higher temperature than that.
And I think Ralph's point was just simply that we can't just simply take the Parker design or even some modification of the Parker design and expect that to work. This really is something that would have to be a new development.
Right, I was pushing on where the limit of the current box was, just for the benefit of everybody on the call here.
I'm not sure if I quite heard the answer. If you eliminated margin, what is the limit of the current design?
Well, I don't understand how to answer that question because I can't eliminate margin. If you're saying I'm going to fly this shield close to the sun, and the shield will either disappear or it won't disappear, as it goes through its flyby, and I'm going to design the shield so that as it's finished with the flyby, there's no shield left. That's the no margin case. That's not even close to practical. And so again, functionally, you're saying I can't eliminate margin along this whole way, and so just allowing for that margin to stay in the system that allows me to launch, because I can't launch with a system that has virtually no chance of surviving, or it does not have a no reliable chance of surviving. I think it's kind of pushing in that 3 solar. If you take the solar probe shield, get rid of the coating and let it get hot, and we're probably in this 5 solar radius range in terms of that where the solar probe shield would get to at.
And we think that
it would start.
Yeah, thanks, Doug. That was really the intent of my question.
Okay.
Okay, next question. There was a comment or question from Jason Minkowski about a cylindrical shield rotating on the axis of symmetry about the rocket motor, for instance, and whether that would be a benefit.
So yeah, so that's a good discussion. And again, as your cylindrical shield, as you're rotating that around, you're basically picking up a factor of 3 in there. On the heating, it depends on how fast you're rotating, a bunch of things like that. So the shield is getting bigger. It's getting more massive. The temperature is, again, these temperatures come down in chunks, and so for instance, if the temperatures, the flux is coming down by a factor of 3, you're still well up there, and so. We had looked at this before, and at least on the, and I don't have a good answer there, but the temperature has to come down far enough that you can change the material. So for instance, on Jim had that chart up, but you have to be able to move from, kind of the refractory metals temperature down into the carbon. So, this is, you're moving from you're taking, so here's a factor of 3. This is 1.1 down to 1.1 down to a little bit 0.4. You're moving 1,000 degrees, 1,500 degrees kind of stuff. It has to get down to the point where you move into a different material range. You have the same problem where now the shield's getting heavier, the heat leaks go into the system. You have to be able to fly to the sun to get out of that process. When you get to the sun, you have to, again, one of the conditions is now you have a cylinder that's flying to the sun. You have to be able to talk to that cylinder. When this thing burns, you're firing a solid rocket motor. The side chunk of that is going into the cylinder. How does that affect the whole thing? So, it is a option. It's got a whole list of its own problems to deal with, and I'm not sure that it solves kind of the principal material ones.
So Doug, and maybe Doug and Jim, Doug, you just made the comment that if you were to go to a cylindrical shield, and you made similar comments earlier about if you were to go this way or that way with the design, that the shield gets heavy and that there's mass and more mass added to make this work. Do we have we don't have, I believe, a parameter that says, even though it gets heavy, this design gets us X AU per year faster, and therefore it's okay that it's heavier.
Well, I think that's the point of the trade study and the concept study we're going to be doing in the spring, is taking all of that, developing what this would have to be given a particular shield construction, and seeing what the speed boost is, whether we get any speed boost, or even if whether the mass is so high that the launch vehicle simply can't lift it.
People might recall, actually, we took the refractory metal design, like is shown here on the screen right now, and made some preliminary estimates on that. And it turned out that your maximum effectiveness was sort of at the order of 4 to 5 solar radii, because as you got into 3, the weight had gone up so much that the delta V had come down so much that you weren't doing as well as you were at 4 or 5. And even at that, you weren't really doing as well as you would with just a simple passive Jupiter gravity assist.
Right.
So that was sort of the conundrum place we are, and that's all written up and documented. And it really illustrates that if you get too close to the sun, you are going to end up certainly losing. I mean, originally when we were talking, the sun's at 5778 Kelvin, and I don't think anybody knows how to take a material that can be in thermodynamic equilibrium with that and have any strength or any mass at all left. And so the question's always been, well, how close can you get? And then the secondary question is, well, what would it weigh? And actually, Leon Alkali and the team out at JPL have been looking at some stuff. And there's a recent publication out from them, and they really came to the same conclusion that once you get in closer, and I don't remember where exactly their number was, but there was really a maximum performance, because as you get too close, your thermal shield constraints way outweigh any advantage that you get from the actual being closer and deeper in the gravity well.
Yeah, and Ralph, I think that makes sense because it's delta V to the 1/2 power and the distance to the 1/4 power, right? So you want the big specific impulse, the big delta V. Getting closer doesn't buy you nearly as much.
Right. Exactly.
And you can also see that, depending on how long the cylinder is, right, you're basically, that is the surface temperature that you're getting to, and you have no place for that heat to go, right? It's radiating on the front and the back end, but those front and back ends are full of things. So, you're basically putting your thing in an oven and hoping that you survive the length of the cooking part.
Yeah, this really is a physics limited. This is a physics limited question. It's not just plain old engineering, and this is one of the reasons that Doug had gotten us involved with ACF, and you know, some very interesting things there, still being, you know, the implications are still being explored, as Doug was talking about. But one of the questions was, well, to what extent has the, you know, high temperature into materials advanced since that we did the original solar probe work that sort of congealed, as Doug was mentioning, about 15 years ago.
So for everybody who keeps tracking this part of the discussion and takes part in the study in the spring, remember that the question here is, if it were to get us faster, how much faster is valuable, and how much would that cost the program? Because amongst our parameters for pragmatic is, we can't come up with something that may be perfectly doable, but is twice as much money as we expect the Science Mission Directorate to be able to apply to a mission like this. And then even if you did say that they had the money for this technology development and this system development, is that money going to actually get us that much more science? Never mind the speed. Is it actually going to get us that much more science value out of the mission?
Yeah, those are all really good questions. I think the good news in all this is we're probably going to hit the physics wall first. We'll see.
But we might hit the physics wall. We might, and if we don't, if we see a 20 or 25% or 50% increase in outbound speed, and it fits on the launch vehicle and all that, it still may need to be a no for the program.
Oh, sure. Well, again, you know, it's just like I emphasized, you know, on our first day of this workshop, we're putting the menu together, and it may be that, you know, you can do a very well done steak and cook it to a charcoal briquette, but nobody may want to order it off the menu.
Now, I don't want to sound like a downer on all this, because I think that in the future of NASA's exploration, there's a place for this. That at some point, our technology, our materials, and the mission that could come from this is very much worthwhile, but it may not be this mission. So,
and that's a really important point to make. And again, if you go back into the solar probe days, solar probe had been thought out, you know, by NASA for decades, right before it actually went anywhere, because, you know, there was how much does it cost for you to, you know, to get going. And a lot of that work was done on the hypersonics, was done in other areas where they had started the effort. They had, you know, they had materials, they had done some testing, they had some analysis, they had done some work. And then you say, well, I'm going to take that body of expertise and I'm going to move it over into this direction. And I'm going to do some work that, you know, that addresses the questions that I haven't, you know, that hypersonics doesn't worry about, but, you know, in terms of how to make a carbon-carbon system, all that kind of stuff, you know, was well known by then. And so now you're talking about, you know, at what point, if you have to start from scratch, you're talking about a long, expensive process. If you're building on something that someone else has done, you're in a much better position.
Just as a quick shout out, so Jason Benkowski, who originally asked this question about the cylindrical shield, is actually working on some interesting propulsion ideas that would use that shield and some waste heat to provide propulsion. So you know, those are things we're keeping an eye on. Again, it comes down to a question of practicality and the time frame that we have to develop a mission like this. But again, there's some very interesting ideas that are out there for potential future missions.
Yeah, come see me at 2:15 on my poster.
Exactly, trying to give you some advertisement. All right, so with that, it's time for us to wrap up. I do want to mention again the Google Doc, so please provide you know, any comments or feedback or suggestions or, you know, criticisms, anything that you would like us to bring to our attention, and we're definitely monitoring those. We'll be responding to those things as we go along. And I think we're going to take about a 10-minute break, and then we'll be coming back to this room for the GNC session, which will have some interesting things to say about how we control for both the solar Oberth case that we're talking about here, and also the cases with the communication system that we were talking about earlier this morning. So that's going to be a really interesting session. And with that, Michael, any final words?
No, just thanks all for the discussion. Doug, thank you for preparing all the material, and Great job, everyone.
Absolutely. All right, thank you very much. I'm going to stop recording and I'll hang out for just a minute and then we'll end the session.